Okay, hi colleagues. In this tutorial video, we are going to talk about how we should be able to teach the lab week 4 uh, lab component. In the record books, the students need to write this under the heading lab 3, and the corresponding theory is present in the module 5 of all the 22 MAT CSM module 5. Okay. The objectives of this lab is to use Python to number one, find the eigenvalues and eigenvectors of a given matrix. The matrix has to be a square matrix. And the next objective, number two, is find the dominant eigenvalue and the corresponding eigenvector by the power method. Now, the power method is an iterative method. It's a numerical procedure which gives an approximate value of the dominant eigenvalue and the corresponding eigenvector. Okay, let's get started. Now, in order to start with this particular objective, we require to use the uh, NumPy library. It provides us with the required uh, ecosystem to to kind of undergo the execution of the objective 1 and objective 2. So for that reason, first of all, we need to import the library NumPy, and according to conventions, we import NumPy as NP. Please make sure to tell the students that instead of NP, any other user given name is also allowed. Okay, so this is appropriately run. Right. Now, the first and foremost challenge here is to input a particular array, the matrix, the square matrix, so in to the computer. And how do we do that? We kind of use the function called array array, which is provided by NumPy. So we call the function array from NumPy using np.array, and then there's a first bracket over here. The first bracket ends over there. Inside the first bracket, we write the matrix in this form. Now, the matrix here is named as A, and it has got three rows. The first row is in the first one-dimensional array mentioned as 432. The second row is the second highlighted line, that is 141. And the third row is 310 4. So these are the three rows of our array, of our matrix, right? We'll call this as an NP array, NumPy array. So once we run that, we can immediately find out that A is nothing but the array containing the first row as 432, right? Then the second row is 141, and the third row is 310 4. Right. Now, accessing elements inside a matrix is done using the list or array searching notation, which is given as here, right? So as you can see, we are trying to find out the first row, third column element. And since indexing in Python starts from 0, the first row is given by the index 0, and the third column is given by the index 2. So the method to write it is first inside square brackets is the index on the rows, and the next we have got a square bracket within which we put the index for the columns. So A12 would be giving us the first row, third column element, which is equal to 2, right? Okay, that's what it is. Right. Now, In order to find out, in order to go ahead with our objectives, objective 1 and objective 2, we require to find out, uh, we require to use a particular module inside the NumPy library, right? And that module is called LINALG, which stands for linear algebra. So NumPy.linalg, that's the name of the entire module, right? This is official documentation for that. It's encouraged that you and all the students go to this particular website and explore what are the different possibilities of using functions and finding out, functions, finding out the solutions to certain problems according to their own branches. But we're going to use certain functions from here. So in the documentation, it says that linear algebra numpy.linalg, right? It says that um, this is an implementation of standard linear algebra algorithms. Okay, now we are not going to use all of these functions, but a certain functions from here. So for example, the matrix eigenvalues can be found by using uh, these couple of functions. So let's try to use linalg.eigvals. This is actually uh, a short form for numpy.linalg.eigvals. We're going to use, and since we have imported numpy as np, we're going to use np.linalg.eigvals. And then in the bracket, we'll mention the variable name, which corresponds to the data type numpy array, in which the data of the given matrix is saved or put, right? Okay. So the way to invoke this function and identify the um, eigenvalues of a particular matrix A, we need to first write E, or maybe it can be any variable name. We are using E because E stands for eigenvalue, but it can very well be X, Y, Z, house, and so on. Okay, so E on the left hand side is equal to NP, that stands for the library, dot linalg. The linalg is a particular module of the NumPy library. EIGVALS, eigvals, is the name of the function that we are going to use. And then there is the first bracket which starts there and which ends there. Inside inside the first bracket, we write the name of our particular matrix. Okay, and then the next line we print out E, and we see that we get an array again. We get a NumPy array. The array has got three elements: the first element, the second element, the third element. Right? So all of these three values are going to be our eigenvalues of the given matrix 4, 3, 2, 1, 4, 1, 3, 10, 4. Okay, now once you are inside this Jupyter notebook, as you know, you can put a question mark in front of the entire module, and then run this cell, which will give a little description of what NumPy linalg is, right? Okay. What we do next is we try to use an alternate function in order to find out the eigenvalues and the eigenvectors. Okay. Now, the way to use this, the way to implement the algorithm is by using the function EIG from the same module numpy.linalg. right? So the way to invoke this is to introduce two variables on the left hand side, W and V. So W is going to contain all the eigenvalues and V is going to contain all the eigenvectors. W comma V is equal to numpy.linalg.eig, and inside the first brackets we write the name of our input, that is the matrix A. Once we run this and we try to print out W and V, we get three eigenvalues in W and three eigenvectors in V. Now the first eigenvector is the corresponding eigenvector for the first eigenvalue. The second eigenvalue is 2.12. The corresponding eigenvector is negative 0.26, 0.14, negative 0.148. And the third eigenvector is negative 0.828, 0.55, 0.89, and the eigenvector is corresponding to the eigenvalue 0.88. So for example, if we want to extract, let's say, the second eigenvector, and of course the second eigenvalue, which is 2.12, we need to use the index 1, because you remember that the indexing in Python starts from 0. So this particular statement will give us the following output saying that eigenvalue is this and the corresponding eigenvector is this. Now, having said that, putting everything together, this particular code prints out all the eigenvalues and the eigenvectors. Also, it does print out the first eigenvalue and the first eigenvector. So putting everything together, import numpy as np should be the first line. This creates the Python ecosystem. A is equal to np array, first bracket, inside that the box bracket or the third bracket. This nesting is done in order to collect all the rows. Next we write all our three rows in form of one particular list per row, and then we print the given matrix. Then we invoke the function np.linalg.eig and inside the bracket A, which will give us in W the eigenvalues and in V the eigenvectors. Then we print all the eigenvalues and eigenvectors, and then we display the first eigenvalue and the first eigenvector. And for that, we use the index 0. Now, once we run this, we get the following output. We get the output that the given matrix is this as per this. The eigenvalues of this particular matrix are these in a list, and the eigenvectors are eigenvector 1, eigenvector 2, eigenvector 3. Now the first eigenvalue is 8.98, which we get over here, and the corresponding eigenvector is as printed out. Okay, now let's move to the objective 2, and the objective 2 was to find out what is the dominant eigenvalue and the eigenvector using the Rayleigh power method. Now the Rayleigh power method starts with an initial approximation x naught and finds out the first approximation x1, And then it finds out the second approximation x2 using the previous approximated value x1, and so on and so forth. Here's an example of the power method in action. So the question says that there has to be 6 iterations of the power method to approximate a dominant eigenvector of a given 2 by 2 matrix. And an initial non-zero approximation of the dominant eigenvector is given by x naught is equal to 1, 1. The algorithm used in each iteration of the power method is given on the left. The new value of x, or the dominant eigenvector, is going to be the matrix A multiplied by the old value or the old approximation of the dominant eigenvector x old. And along with that, there will be some other small terms which we will ignore. And since it is a numerical method, it's okay to ignore the other small terms. In this example, the iteration 1 gives a particular matrix, particular vector. In this vector, the eigenvector is 2.51 and the corresponding eigenvalue is -4. This way, the iteration 2, 3, 4, 5, and 6 are done. Let's go back to our code and discover a few important checkpoints. So as you had seen in the previous picture, that we need to use matrix multiplication. And the matrix multiplication is often referred to as the dot product, because all calculations here are scalar. The dot product using Python is extremely easy. For that reason, let us initialize two arrays or two vectors, 1 to 3 and -1, -2, -3. And we name them as small a and small b. Let dp be the dot product. Again, this is the name of a variable, and it can be named c, d, e, f, anything as per the user's choice, making sure that the name of the variable hasn't been repeated. dp, the dot product, is obtained by numpy.dot or np.dot. This function takes in two parameters or two arguments. The first argument is the first vector, and the second argument is the second vector. np.dot open bracket a comma b close bracket is going to give the dot product of the vectors a and b. Once we run that, we see that the dot product of 1 to 3 and -1, -2, -3 is -14. This product can also be used to find out the product of a matrix and a vector if the multiplication is possible. So let's define a 2 cross 2 matrix A, np.array. The first row is given by 1, 0. The second row is given by 0, 1. This is the matrix, which is also known as identity matrix. So this matrix, when multiplied by a vector 2, 3, which is defined as np.array first bracket box bracket 2 comma 3 box bracket close first bracket close, using np.dot in the bracket a comma c, we get 2 comma 3, which is true, right? Because once we multiply a vector with the identity matrix, we get the vector back. Okay. Now, in order to use the power method to find out the dominant eigenvector and the dominant eigenvalue, we define a function called normalize, which uses the product AX old and gives us a new value of the new eigenvector. So what happens is that the matrix times the old eigenvector value is probed and the highest absolute value is obtained. Which means that if there are elements -3, 1, 2 in a three-dimensional eigenvector approximation, we take the absolute values of each of the elements -3, 1, 2, consider them as positive numbers 3, 1, 2, and identify which has the highest value, which is 3 in this case. So the new eigenvalue is going to be equal to 3 when the old eigen when the product of the matrix with the old eigenvector gives -3, 1, 2. When the product of the vector of the previous eigenvector -3, 1, 2 with the given matrix A are multiplied with each other, then the new eigenvector is obtained by finding out the largest element considering the negative symbols from this vector, from the product vector. So -3, 1, 2 has the largest element as 2. So what we do is that we multiply the product vector by the reciprocal of the largest element in the vector. So -3, 1, 2, the elements of this particular vector, will each be divided by the largest value between -3, 1, and 2, which is 2. So we get the new eigenvector as -3 divided by 2, 1 divided by 2, 2 divided by 2, which is equivalent to the matrix, to the vector, to the new eigenvector, -1.5, 0.5, 1. Now let's see how this can be implemented in our program. For that, we need to define a function called normalize, which takes an argument x. FAC is going to be the maximum value of all the absolute values of the vector x. X underscore n is going to be an array which is same as dividing each element of the array x by the maximum value in the array x. The arrays here are the vectors. Once we run this and consider x1 to be a dummy variable containing a vector negative 0.8, 0.1 and negative 0.2 as an example, we get the following output. 0.8 will be the new eigenvalue and negative 8, 1, negative 2 will be the new eigenvector. Using this normalized function, we're going to compute the eigenvalue and eigenvector of a matrix. So let's say that the given matrix is small a this time. The way to define a matrix is to use np.array. And within the first bracket, we must give our two-dimensional array. It's called a two-dimensional array because the first dimension is controlled by the first square bracket, which is the list of all the rows. The first row is 113, the second row is 151, and the third row is 311. We need to find out the largest eigenvector of this particular matrix. For that, we need an initial approximation, and we take the initial approximation as 111. And we save this particular vector in the variable x. Now, let's come to the final loop, which gives us a little purview about how to go ahead with this problem. Firstly, we need to specify the number of iterations. In this case, we are using 10 iterations. So for that reason, the entire process of multiplying the matrix by the vector and then from the product extracting the eigenvalue and the corresponding eigenvector will be done using the normalized function. So the two steps are, we will update the eigenvector as np dot dot a comma x, which gives the product of the matrix with the old eigenvector. The product is then subjected to the function normalize, which we have defined earlier over here. And the outputs of this normalized function is going to be the eigenvalue, and we represent that by lambda underscore 1 because lambda lambda is a keyword. So we cannot use lambda as the name of variable. So we use lambda underscore 1 to identify the eigenvalue obtained at this stage. And we use x to denote the finalized new eigenvector. Now the students might argue, And colleagues, they might ask you, why is X being used here and here in both these lines? This is done to make our program more efficient and not to overburden the memory space in the compiler or in the server or on the computer itself, right? So hence we reuse the same variable. Moreover, whatever variable name we write on the left is going to have a final value. If the same variable name is used on the right, the previous value of that variable will be called. Now, having said that, we see that we have used a for loop here. This for loop is used to execute the two lines in this indentation block 10 number of times. Once we reach the end of this 10th step, lambda1 would have been updated 10 times, and this x would have been updated 10 times by the normalize function and 10 times by the np.dot function. So the final value after 10 rounds of these two steps would be the result of the 10th iteration. And that is exactly the values that we are printing out. We're printing out the eigenvalue as lambda1 and the eigenvector as equal to x. Mhm. And that's the result. This is the largest eigenvalue, and this is the largest, it's corresponding eigenvector for the largest eigenvalue. Okay, the next method is an alternate method, and it has been left for the reader to explore and discover. Thank you.